Okay, greetings. This is session number 2 of Math 120 for Southern California Seminary. I hope you can hear me correctly and everything, audio and video are working properly. If not, please contact me. Well, let's start with prayer and then we will go to our lesson. Father God, we thank you for another opportunity to study mathematics and learn it's just a manifestation, a small portion of your wisdom and your beauty, your glory, and the pattern that you have created this world, because we can see a mathematical pattern in this world that all point out to your infinite wisdom, knowledge, and glory and majesty. I ask your blessing upon all the students in this class, for all not only for this course, but for all the courses that you are taking. May you bless them, use them mightily for your glory, and keep us usable and provide for their needs. May they do excellent in this course and in other courses that they are taking. Help us to be diligent in our study for your glory. For in Jesus' mighty name we pray. Amen. All right, let's go to our PowerPoint. We're continuing studying of our topic of mathematics, session 2, Math 120, and tonight we are going to study about sets. Let me make this bigger. We're going to talk about set of numbers. We use sets in every day of our lives in different shapes and form. What is a set? Set is a collection of objects which are called elements or members of the particular set. A set is well defined if its contents can be clearly determined, if its contents can be clearly specified. There are 3 methods are commonly used to indicate a set: a description, roster form, and set builder notation, that we will talk about them. Description of a set. Write a description of the set containing the elements of Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Well, the set is a day of the week. That's the answer. This is a set of the day of the week. Listing the elements of the set inside a pair of braces is called a roster form. So when you just describe it, this is a set of days of a week, you're giving a description of the set. Then you can also describe it in a roster form. You put the elements of the set within a pair of braces. For example, you have here, you have a pair of braces, and then we have 1, 2, 3. This is a roster form notation for a set. For the set whose the elements are 1, 2, and 3. But this within a parentheses or brackets are not set, because parentheses and brackets do not indicate a set. Sets are generally named with capital letter. For example, the name commonly selected for the set of natural number or counting number is capital N. So we have a set of natural number, 1, 2, 3, 4, 5 to infinity, and we use the capital N to identify it. The 3 dots after 5 are called ellipses, indicate the elements in this set they continue in the same manner. The roster form, we want to express the following in a roster form. A set A is a set of natural number less than 5. Set B is a set of natural number less than or equal to 75. Let's go on. For example, for set A, the set of natural number less than 5. Okay, if we want to express it in a roster form, it includes number 1, 1, 2, 3, and 4. Less than 5. Natural number. It cannot have negative numbers. And it cannot have fractions. 1, 2, 3, 4. And we put that in braces like this. This is explaining it in roster form. The second one, set B, is a set of natural numbers less than or equal to 75. So again, you write B equal to 2 braces, 1, 2, 3, 4. Then you don't need to write all those numbers. You put the 3 dots, the ellipses, up to 75. It's a set of number less than or equal to, so it includes 75. The set P is a set of planets in the Earth's solar system, so which includes Mercury, going from sun, after the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We used to have Plato, but that was counted down because they don't consider Plato as a planet anymore. It's called a dwarf star. Okay. The word inclusive, for example, we express the following in a roster form. The set of natural number between 4 and 9. You see, it's between 4 and 9. So it doesn't include 4 and it does not include 9. It's set A. Again, you put the braces 5, 6, 7, 8. Now, you want a set of natural number between 4 and 9 inclusive, then you include the 2 ends, the numbers 4 and 9. 4 and 9 are also included in this set. Set builder notation. Oops. Set builder notation or set generator notation may be used to symbolize a set and is frequently used in algebra. The symbol, you know, it's look like a E. Red is, this means it's a part of, it's an element of a set. For example, if you have a set A that it has these elements, 5, 6, 7, 8, we can say 6, and then we use this symbol, is a part of set A. 6 is part of 5, 6, 7, 8. When, for example, a number is not part of a set, like number 9, we use the same number E, but then you can see there's a cross. A9 is not an element of set A. This is set builder notation. Basically, in set builder notation, you have the braces. It says the set of all the x such that you have this little bar, x is less than or equal to number 2. Less than or equal. On the table 2.2, you have all these, for example, here, x is less than a, x is less than, and then if you want, this is symbol, this is description. If you want to write it as a set builder notation, you write a set of x such that x belongs to natural numbers and x is less than 4. Therefore, it can only be 1, 2, and 3. But if it's set of a less than equal to a, then you write set of a, set of x such that x belongs to natural number and is less than equal to 4, then it includes number 4. All right? Excuse me. Let's look at, for example, this one, the last one. X greater than A, but less than or equal to B. And you see this sign, the mouth is toward X, means greater. X is greater than the A and less than or equal to B. So we are looking for set of X such that X belongs to natural numbers and is greater than 4 and less than or equal to 8. So the natural number would include 5, 6, 7, and 8 is great. They are greater than 4 and less than and equal to 8. But if you see here, for example, the one above it, it says greater than equal to 4, so you have 4 here, and less than 8 doesn't include 8. All right? Continue. Cardinal number of a set. The cardinal number of a set represents n of a is the number of distinct elements in the set. The symbol n parentheses a is read n of a. The cardinal number answers the question of how many. For example, let's look at page 50. Example number 8. If you look at your textbook, please, you can see that like the first one talks about a set A is equal. It's a set of numbers that its elements are 7, 9, 11, and 13. What's the cardinal number? How many elements are in that set? 4, 7, 9, 11, and 13. So the cardinal number is 4. Maybe if you need to see that, I can show it on the board. Okay, let me then go here. Okay, let me show you here, and I will try to speak loud and clear so you can hear me. We have a set 7, 9, 11, and 13. 7, 9, 11, and 13. To find the cardinal number, just count the number of elements. 1, 2, 3, and 4. So the cardinal number of this set is 4. If this is called set A, n of A is equal to 4. Okay? Let's look at set D. Or actually, let's look at set B first. Okay. Make sure it's recorded correctly. Okay, set B. My board is falling. Okay. We have set B 0. Okay, what's the cardinal number? Has one element. 0 is one number. 0 is a number. So the cardinal number n of B is 1. Then we have set number D. We have a set which is an empty set. Null. This is a symbol for null or empty set. The cardinal number of this set, if it's, give it a name, D, n of D is 0, is an empty set. Okay, but 0, remember, 0 is a number. So if the set has only 0, its cardinal number is still 1. Okay. All right. Let's see if there's anything else. can go back to share. Okay, we talked about that. Let me make it bigger. The cardinal number. Finite and infinite set. Set A is a finite set if n of A is 0. That is, A is an empty set, or n of A is a natural number, any of the natural number. A set whose cardinality is not 0 or a natural number is called an infinite set. You see, if it's the cardinal number is not 0, it's not an empty set, and it's not any natural number, because if it's 0, it's still if the element of a set, if the only element in the set is 0, its cardinal number is 1. But if set A is a finite set, it's called a finite set if n of A is 0. The cardinality of set is 0. Or it's a null set. Or if it's any natural number, it's still a finite set. But if the cardinality is not 0, it's not an empty set, and it's not any of the natural number, then it's an infinite number. For example, let's consider this set. It's 1, 2, 3, 4, 5, 6, and 3 ellipses. It means it continues. There is no final element. This is an infinite set. A universal set is all the elements or members of any group under consideration. For example, a universal set for students of Southern California Seminary includes all the students, part-time, full-time, whatever their age. They're all in that universal set. A cardinal number is finite and is signed as symbol of aleph null. The cardinal number is the cardinal number is infinite when the cardinal number is infinite and is signed as a symbol aleph null. Okay, this Hebrew aleph, and then you have this null. This is cardinal number for an infinite set. For example, set n, 1, 2, 3, 4, 5, 6, which continues to infinity, its cardinal number is infinite. It is symbolized by aleph null. Okay? Equality of set. All right. Set A is equal to set B means that set A and set B contain exactly the same element, regardless of order or possible repetition of elements. Is symbolized when two sets are equal as A equal to B. For example, if you have set A equal, these are these elements, W, X, Y, Z, and set B is Z, Y, W, X, they are equal because they contain the same elements even though the order of elements are different. Let's look at example 10, page 53. Example 10. For example, it gives us first, please look at your textbook, example 10, page 53. You have set A 4, 8, 9. It's asking, is it equal to other one, 8, 9, 4? Yes, because they contain the same element. Now look at set B, then number B. Yeah, on one side you have 1, 3, 5. On the other side you have 0, 1, 3, 5. So no, they are not equal. The second set doesn't have, it has 0, which the first one doesn't have. 0 is a number, all right? Let's continue. Then we come to subset. Set A is a subset of set B symbolized, as you can see here, if and only if all the elements of set A are also elements of set B, but the reverse may not be true. The reverse is not true. Yeah, what I mean is, it doesn't mean that all the elements of set B are in set A. Only all the elements of set A must be in set B. Set A is not a subset of set B, then it's symbolized by this. Let's look at example 1, page 57. For example, example 1, page 57. Please look at your textbook. You see the number A asks, set A is 1, 3, 5, 7. Set B is 1, 3, 5, 7, 9, and 11. Set A is a subset of set B. Now, let's look at B. A is all the X such that X is a letter in a word proof. Now, set B is Y. Y is a letter in a word roof. Now, it's asking, is A subset of B? Well, let's look at it. A contains PROOF. Well, set B has ROOF, but it doesn't have the P. So A is not subset of B, but actually B is subset of A because all the elements of set B are in set A. Look at C. X such that X is a planet of Earth's solar system. Set B is Mercury, all those planets. So yes, set A is subset of set B. Okay. I hope this is clear. Let's move on. We come to proper subset. If set A is a subset of, but not equal to B, to set B, A is not equal to B, then A is called a proper subset. For example, let's look at page 58. On page 58, set A, please look at your textbook. You have 1 and 3. Set B is 1, 3, and 5. A is a subset of set B, and it's a proper subset. They are not equal, and all the elements of set A are in set B. Then set A is a proper subset of B because A and B are not equal sets. And notice when they are proper subset, we use this symbol. But if, for example, we have set A 1, 3, and 5, set B 1, 3, and 5, then set A is subset of set B, and every element of set B is also element of set B. They are equal, therefore it's not a proper subset. So we use the symbol, we don't use this symbol, we use this one. Okay? Let's go example 2. Checkpoint 2. Okay, example 2. If you have set A, X such that all the X is a person and X lives in San Francisco. B, X such that all the X is a person and X lives in California. A is a proper subset of set B because all the people living in San Francisco are also part of living in the state of California, unless our legislature changed the state map. Okay, but as of now, yes, all the people who live in San Francisco are part of set B, and they are not equal. So it's a proper subset. So we use this symbol. Okay. Then set B, I'm sorry, number B. Set A has 2, 4, 6, 8. Set B has 2, 8, 4, 6. They are equal. They are not proper subset. A is not a proper subset of B because all the elements of A are in B. They are equal sets, so we don't use this symbol, we use this one. Okay, as you can see on your textbook. So for a proper subset, we use this. When they are all the elements of set A are in set B, but they are not equal. For when the two sets are equal, we use this symbol. All right. Empty set as a subset. The empty set is a subset of every set and is symbolized by this null. The empty set is a proper subset of every set except itself. For any set B, an empty set is part of that because it's nothing. For any set B other than the empty set, other than the empty set is also it's also a proper subset. So null is an element of every set, and it's also is a it's a proper subset of every set except itself. Let me repeat this. I know it can be confusing. Empty set is a subset of every set and is symbolized by null. The empty set is also proper subset of every set. So if you have a set B, null, the empty set, it's proper subset because it's a part of every set, but they are not equal. But it's but empty set is a subset of every set. Okay. For any set B, any null is an element of that. For any set B other than the empty set itself, it's a proper subset. Okay, you follow me? Because it includes in B. So let's look at complement of a set. So we have A and A prime. The complement of set is symbolized by A prime is a set of all the elements in a universal set that are not in it. If we consider this rectangle as a universal set, here's a set A. Whatever is not in set A is A prime set. These two are complement because when together they form the universal set. When we have you have three sets, and then we find the intersection of them, we use this symbol as this yellow part is the intersection between set A and set B. This purple part is the intersection between set A and set C. This blue part is the intersection of B and C. And when we have A, B, and C, then we have this, this is white part is the intersection of all the three subsets, all the three sets, I'm sorry. Okay. Now we talked about intersection, we also have union. Union of A and B is the same as union of B and A. Union of set A and set B is symbolized by A, U, B. Is a set containing all the elements that are members of both set A and set B. Union operation. Then this is called Venn diagrams. You have set A, set B, set C. Set A consists of little a, D, G, and E. B, D, G, and F. And C is little c, E, G, and F. Outside, there's not. The total. It gives you the total diagram. You know, these diagrams are helpful in ministry when you want to study your congregation or the people that you're ministering. You can find, for example, different people, different age group, different level of education, and you can do a study about how they are doing church attendance, how they are doing with their devotional life. You know, these have useful application in church ministry. Now, for example, consider each friend as an element. You have a team that plays soccer, another team plays tennis. The soccer team has Alex, Casey, Drew, and Hunter. Tennis, Casey, Drew, and Jade. Okay? So we have two sets. The union will be all of them together. Alex, Casey, Drew, Hunter, and Jade, all 5 of them. This is a Venn diagram. It's a total of all. The Venn diagram, you remember here, right here. The total, okay? Now, intersection would be the one that are in both groups. The one that are in both groups, let's go here. We only have Casey and Drew. Okay, this is the intersection. The difference, soccer minus tennis, the people who are only in the soccer but they are not in the tennis are Alex and Hunter. Okay. So U is union, is in either set. The reverse of the upside down is the intersection, must be in both sets. The difference minus in one set but not the other. Okay. Let us say the third set is volleyball, which Drew, Glenn, and Jade play. So we have volleyball set, Drew, Glenn, and Jade. The S means the set of soccer, T means the set of tennis player, B means the set of volleyball player. So this is the, again, Venn diagram. You have these 3 sets, S, soccer, tennis, and V, the volleyball. Drew plays all of them. Jade plays tennis and volleyball. Alex and Hunter play soccer, but they don't play tennis or volleyball. And no one plays only tennis. Everybody plays tennis plus something else. Okay, as you can see, like Jade is in tennis and also in volleyball. Drew is in tennis, volleyball, and soccer. Let's look at set S. Is Alex, Hunter, Casey, and Drew. This is just a set. It's Alex, Casey, Drew, and Hunter. Union of set T and V, the tennis and volleyball, would be everybody who plays both tennis and volleyball. Casey, Drew, Jade, and Glenn. Intersection of set soccer and set volleyball, the person who is in both of them is only Drew. Okay. Okay, now what is this empty set? The intersection of set S and set S and set V minus T, meaning the person who plays both soccer and volleyball is Drew, but does not play tennis. So Drew does play tennis. Drew is in tennis. So it's an empty set. Okay. Again, we have intersection of set S and set volleyball, set V. The person who plays both of them, which the person who plays both soccer and volleyball is Drew. But then we want to find a minus set tennis, meaning a person who plays both soccer and volleyball but doesn't play tennis, then you get an empty set because Drew does play tennis. Okay? Universal set is all of them together. Alex, Blair, Casey, Drew, Erin, Francis, Glenn, Hunter, Ira, and Jade. All of them together. Soccer, tennis, volleyball. And these four guys, these four person, who are outside, they are not part of either of these three teams, but they are part of the universal set. The part of the, they would be the prime of these three sets. The prime of the union of these three sets. Let's say if there's a school, for example, and it has only these students are in these sports team, but these four are not in any of them. But together they form the universal set of that school regarding the students. All right, everyone who does not play soccer. So you want to find everyone who doesn't play soccer. So it includes the universal minus soccer. So you take the soccer and subtract it from universal. We get Blair, Erin, Francis and Ira, Glenn, and Jade. Everything that is not S prime, everybody who does not play soccer. So you only have Jade, Glenn, Blair, Erin, Francis, and Ira, written as S prime. Again, let's look at page 68, example 3. It says, finding a set complement. Let U be 1, 2, 3, 5 through 9, A be 1, 3, 4, and 7. Find A prime, okay? So, first of all, we look and see A prime contains all the elements of set U that are not in set A. Okay. If you want to find A prime, so if it's set, you have set U. Set U is 1, 2, 3, 4, 5, 6, 7, 8, 9. And set A is 1, 3, 4, and 7. Set A is proper subset of set U. We want to find A prime. So whatever it's not in A. So we cross A, number 1, because 1 is in A. We cross number 3, we cross number 4, and we cross number 7. So if U is a universal set, then A prime would be 2, 5, 6, 8, and 9. Okay, and you can see the Venn diagram right next to it on page 68. Okay, so there you have the universal set, then you have A prime, whatever is not in A, but it's part of the universal set. Okay. Why are sets important? They allow us to treat a collection of mathematical objects as a mathematical object as itself. The starting point to any mathematic is the definition. And without set, we would be hard-pressed to give definition of most mathematical objects. It's part of the language, part of the vocabulary of the language of mathematics. That's why it's important to learn about sets, subsets, proper sets, and all those intersection unions. Definition relying on set. For example, function is a rule that maps numbers to other numbers, but what does a rule mean? It can seem quite vague at times. That's why we need to understand sets and subsets to understand the meaning of the word rule. For example, is 2x the same rule as 2x plus 1 minus 1. They are different rules in that they are calculated in different ways, but they always yield the same output. Hence, we define a function as a set of ordered pairs. Function does have a rule, but it has ordered rules. For example, here, this is 2x and 2x plus 1 minus 1. The outcome, whatever you put in x, would be the same, but the process is different, because here when you put, let's say I put 3 for x, I have to first multiply 2 by 3, 6, before I add and subtract here. But here, no, just you put 3 and you get automatically number 6. In chapter 6, we'll address domain of function. A function maps numbers to numbers, but the same concept of rule that maps things to things pops up all over. Additionally, operators map functions to numbers. Mathematical operation in groups maps abstract group element to other elements. And other strange function might map equivalent classes of infinite sequences to finite set of rational numbers and so on. But you cannot precisely pin down what things means unless you have a mathematical notation, you understand the vocabulary, you understand the meaning of these vocabulary. You have mathematical notation and you understand what do they mean. Algebraic structure or topological space are both considered a set with operations on them. The whole power of modern algebra is that it can apply to set of things, set of different sets, subsets, or whatever, as long as the operation contains rules. Now, let's go to chapter 4, number representation and calculation. Throughout history, human beings, different human civilizations have different numerical systems. We use Hindu or Arabic numerical system. Okay. The number system or system of numeration consists of set of basic numerals and rules for combining them to represent numbers. We have place value, we have positional value. The value of symbol depends on their position in the representation of number. For example, 2 in 20 represent 2 tens, and the same 2 in 200 represent 200s. In other words, so the position of number 2 tells us different values, gives us different numbers. A true positional value system requires a base. Our base, we use base 10, and a set of symbols, including a symbol for 0 and 1 for counting number less than the base. One of the great advantage of our numerical system, the Arabic numerical system, is we have 0. And that is the reason that cultures who adopted this system have advanced. And that's why the other numerical system went out of existence, for simple fact that they didn't have 0. Now you will see that, because in numeration, it makes it very difficult if you don't have a symbol for 0 and 1. The most common positional system is base 10 system, which is called decimal number system. Decimal coming from the word deca in Greek, meaning 10. Hindu-Arabic numeration system. Hindu-Arabic numeration system requires fewer symbols to represent numbers as opposed to other numeration system. In this system, these digits 0 to 9, you can make all kind of numbers with, just with these 10 digits. Numbers from 1 through 12 have unique names. 1, 2, 3, 4, 9, 10, 11. 12. Then from 13 through 19, we have teens as ending. And the ending is blended with names for numbers 4 through 9. 4, 5, 6. Okay. For numbers 20 through 99, the 10th place is named first, followed by a number from 1 through 0. And for example, we say 30 or 35. Numbers from 100 through 999 are a combination of hundreds and previous names. So 0, 1, 2, 3, and 15, 20, and it goes on. We have also exponential notation, very important in mathematics. If n is a natural number, 1, 2, 3, 4, and so on, then we write b to power of n, meaning it's b times b times b times n times. Now, for example, if b was 2, we multiply b 2 times. N is called exponent. B is called the base. B exponent n, or b to power of n, the n power of b. The expression bn is called an exponential expression. B to power of 1 is b. B to power of 0 is equal to 1. Any number to power of 0 is equal to 1. So again, this is called base. This is exponent. We read that b to power of n. This is exponential expression. Let's look at page 195. Example 1. So, okay, let me, you can look at it on your textbook. Please go to page 195 and see, for example, example 1, you have 10 to power of 2. The exponent is 2. Maybe I better show it here. So if we have 10 that, find one that it does work. Maybe I put on markers. Go. Oh, here. We have 10 to power of 2. 10 to power of 2. Okay. This is base. This is the exponent. 10 to power of 2 means 10 times 10. 100. Okay. Let's different numbers, 10 to power of 4 is equal 10 times 10 times 10 times 10, or 10,000. 10 to power of 1 is 10. 10 to power of 0 is equal to 1. Any number to power of 0 is equal to 1. Okay. You can look at page 195 and see example 2 and see these examples. So let's continue. Positional value is very important in any numerical system. Positional value in Hindu-Arabic systems are, for example, it starts from this side, you go from right to the left, 1, 10, 100, 1,000, 10,000, and so on. To evaluate in numerals in a Hindu-Arabic system, we multiply the first digit on the right by 1. We multiply the second digit by 10, the third digit by 1,000, the fourth digit by 10,000, and so on. So the position of the number, like the 20 that we looked at it, 20, the 2 is in the second position. It means 2 tens, okay? Numeral in expanded form. In general, we multiply the digit n places from the right by 10 to n minus 1. Therefore, for example, we multiply the digit 8 places from the right by 10 to power of 7. 10 to power of 7, what do we mean by that? Let's say if you have, let's look at this expanded. If you have 1, this is 1,234, okay? So we have 4 digits, 1, 2, 3, and 4. 1, 2, 3, and 4. This is in position, the first position, remember? Last slide. This is position 1, okay? So we multiply this one by 1. The second one by 10. Third one by 10 to power of 2. The fourth one by 10 to power of 3. And when you add them, you get the same value. This is an expanded form of 1,234. So in the quiz, in the test, when I ask, please write in an expanded form, that's what I mean. Please understand. Using the place value rule, we can write a number in an expanded form. In general, from right, we go to left by 10 to power of n minus 1. Okay? So this is, you get a number, 1,234. Just pick the digits, 1, 2, 3, and 4. 1, 2, 3, and 4. This is in the first place, so multiply by 1. This is in the third place, so multiply by, this is in the second place, I'm sorry. So multiply by 10. This is in the third place, so multiply by 10 to power of 2. So it's n minus 1. This is in the third position, okay? Third position, multiplied by n minus 1, multiplied by 10 to power of 2. So you take the position, call it n minus 1, multiplied by that number. This is in the fourth position. So 4 minus 1, 3. So multiply by 10 to power of 3. Okay? All right. Let's keep moving. Babylonian numeration. These are there. Just think of trying to make calculation using these kind of symbols. That's why these numeral system went out of existence. Babylonian system, the oldest known numeration system, but it was out of date. It was base 60. sexagesimal system. That's what it's called, sexagesimal system, base 60. Not a true place value system because you had no value, no symbol for 0, which leads to lots of confusion and ambiguity. And that's one of the reasons that this kind of system and the one like it went out of existence. The positional value in Babylonian system are like this. This is just have to know it by memory. The first one 1, the second one 60, the third one 10 to the power of 2, the fourth one to power of 3. Let's, for example, look at page 198. Example 4. If you look at page 198, oh, 197, I'm sorry. Page 197, example 4. It says, write each Babylonian numeral system as a Hindu-Arabic numeral system, like the one that we have. And then it gives us number A. You look at A, and remember that positional value. You have, yeah, I guess I better show it to you on the board. For example, the number A, again, I will make sure I speak loudly so you can hear me. You have these two symbols, these like V's, V, small v. Now, you have to look at the table 4.1 to know what that means. That means two, it's a symbol for 1. So this is symbol for 1. Then we have this symbol and that symbol. Okay. The other symbol, the symbol for 10, but the place is 60. And then we have, oops. 2V, I mean, 2 of these side V's and one of these. Oops. Sorry. Okay. Now it tells us these symbols, these small v, which I hope you can see, means for 1. So we have parentheses. Let me write it with different color to make it more clear. So it's 1 plus 1, because based on table 4.1, these are symbol for 1. 1 plus 1, but then you need to know the positional place, the positional value. This is on the third position, so it's times 60 to power of n minus 1. Third position, minus 1 to power minus 2, power of 2. Then we have this symbol, okay? That means this is a symbol, again, based on table 4.1. That's a symbol for 10. And this is a symbol for 1. So we have 10 plus 1. This is in a second position, times 60 to power of second position, n minus 1, 2 minus 1, power of 1. And the last one, two of these side V's, each of those are 10, so we have 10 plus 10 plus V, which is symbol for 1. No, this is on the first position. This would be so when it's in the first position, then you have multiplied by, it's 60, first position, n minus 1. 1 minus 1 is 0. Any number to power of 0 is 1. So we multiply by 1. Okay. So this is number 60. This is the first position. 1 minus 1 equal to 0. So any number to power of 0 is equal to 1. So this becomes 1. All right. Hope you can see that. One, 1. Third position, so 60 to power of 2. 10, 1. Second position, 60 to power of 1. These sides, 10 symbol, 10 plus 10 plus 1. First position, 60 to power of 1 minus 1 is 0. Any number to power of 0 is 1. Okay. So you just then multiply and add. You convert it to the Hindu value system or Arabic value system that we have here at the bottom of page 197. That symbol is equal to 7,882. All right, let's continue.